Hello everyone, this is Dr. Anas Abu Talib, and I am here to present the paper titled Utilizing Minimum Spanning Trees for Effective Mobile Sync Routing in Wireless Sensor Networks. The presentation will proceed as follows. We will start with an introduction of the topic and a problem statement. After that, a sample of related work will be presented. An overview of Prim's algorithm would be presented next. Then the proposed model of the paper mentioned will be discussed, along with the simulation scenarios and results. And after finally the paper will conclude. Wireless sensor networks have numerous applications. Most of them or some of them are dependent on mobility, such as emergency and seismic recovery applications, field surveillance applications, animal monitoring, and law enforcement applications. These applications need sensor nodes to be designed to be small, lightweight. As a result, they will be limited with limited energy sources. Also, due to the hostility environments in some applications, the wireless sensor networks are expected to operate in an unattended manner for long periods of time. As a result, the major issue here is to keep the network working and prolong the network lifetime as much as possible. One of these one of the techniques used is to introduce the use of a mobile sync to collect data from stationary sensor nodes in order to reduce the amount of energy that is used to transmit data for to the mobile station or to the base station, sorry. Uh, as a result, using a mobile sync will affect the network topology because the communication links and connectivity will keep changing during the lifespan of the network. As a result, we need a sync mobility model that will keep these changes as minimum as possible while preserving some other capabilities such as self-organization and fault tolerance for sensor networks. Also, this mobile sync must collect data from stationary sensor nodes in timely manner. In other words, it should not take too much time to visit a sensor node. As a result, the data stored in that node will be outdated. Also, the period of time should not be long for the visit. Otherwise, a sensor node might suffer from buffer overflow. In this slide, we will talk about some of the related work papers. Uh, Basically, the mobility models were presented in the literature were divided or can be divided into two main types. The first one involves using a single sync to collect data from fixed or stationary sensor nodes, while the other is based on providing every sensor node the ability to move and change its location. In our work, we focused on the first group because it is more related to the work presented, because the paper is based on providing a single sync that will move throughout the network in order to collect data from stationary sensor nodes. Several mobility models were proposed. As an example of them, we have Kionen's self-organization map-based model and by pyrotograph-based model. Uh, Both models are based on on the mobile sync having the following behavior. Regardless of the way the mobility model is created or constructed, the movement of the mobile sync is divided into rounds. or the first round is can be called movement round, while the other round is based can be called pause round or pause period. In other words, the mobile sync will start in with the pause period, so it will stay in its current location for a specific period of time. After that, when this period expires, the movement period is initiated, and the mobile sync will collect or will start moving to a new location based on the algorithm used to construct the mobility model, and will move to a new location. Upon arrival to the new location, the mobile sync will enter the pause period again, and so on. For the Keonan self-organization map, the Keonan self-organization map is a special class of artificial neural networks known as competitive neural networks paradigm. The main idea behind self-organization map is to establish a topological relationship of input data using a learning scheme known as competitive learning. In this scheme, the output neurons that are fully connected to input neurons compete among each other in order to get activated based on the input value. Output neurons compete to get activated, and only output neuron uh, one output neuron wins the competition and gets activated. To elaborate, for each input pattern fed to the map, all neurons calculate values to determine the degree of similarity according to a determinant function. As a result, the most similar neuron to the input value is considered to be the winning neuron. If we want to talk about this from a sensor networks context, the most similar neuron will be the nearest node. As a result, the nearest node will win the competition and get visited by the mobile sync. For the biparity graph is based on dividing static sensor nodes into two groups based on the relations or the distance between them. So the near node will be in the same group. Uh, in general, the network will be divided into two groups, and the mobile sync will start with one group and visit all the nodes in that group. Upon finishing visiting all the nodes in that group, it will move to visit the nodes in the other group, bearing in mind that the movement of the mobile sync is divided into pause periods and movement periods as mentioned above. To talk about the basis of the mobility model that was proposed in this paper, we will give an overview of Prim's algorithm. Prim's algorithm is one of the greedy algorithms that are used to build a minimal spanning tree from an undirected weighted graphs. The approach used is to find the smallest cost tree that covers all the graph vertices without omitting any vertices. The Prim's algorithm can start from any vertex and will start adding edges with the smallest weight for that vertex. If we look at the figure below, the part A represents a randomly deployed network, and part B represents the minimal spanning tree that was derived from the network in part A, starting from node or vertex 4. Uh, Having said so, the proposed mobility model is based on building a minimal spanning tree using Prim's algorithm as follows. Basically, the model is based on a randomly deployed network with one mobile sync. After the network is deployed, all the nodes, including the mobile sync, will send their positions to the base station. The base station will compute the minimal spanning trees taking the nearest fixed sensor node to the mobile sync as the root of the minimal spanning tree. If we look at the previous slide, so if we assume that node number 4 is the nearest node to the mobile sync, then the minimal spanning tree will be built according to this sequence. So starting from node number 4, then 3, 1, then 2, then node 7 is visited, 6, and 5. After that, this sequence will be given to the basis to the mobile sync, and the mobile sync will visit the nodes according to this uh, sequence. For the simulation, NS2 simulator was used to simulate the proposed model in order to test the mobility model under heavy circumstances uh, or heavy traffic. Constant bitrate traffic model was utilized. The simulation covered networks with different sizes: 26, 51, 76, 101 randomly distributed nodes in 1000 by 1000 grid in order to uh, test the performance of the mobility model under different densities and network sizes and under different speeds. As you can see, the speed of the mobile sync was varied from 5 to 20 meter per second. Uh, Also, average one-way delay, packet delivery ratio, and throughput metrics were used to evaluate the performance of the suggested mobility model. In the next slide, we show the performance of the average one-way delay for the network uh, for different sizes and mobile sync speeds. It can be observed that the best overall one-way delay results were obtained by networks with 51 and 76 nodes, particularly when the mobile sync speed was 10 meters per second. This kind of behavior can be attributed to the fact that the mobile sync is operating at a pace that is deemed moderate, merging the utilization of single hop and multi-hop transmission to achieve low one-way delay values. When it comes to packet delivery ratio, also it is clear from from the figure that the suggested mobility model achieved unswerving performance across various network sizes. Also, the results are consistent with the findings from average one-way delay, where networks with 51 and 76 nodes demonstrated the best performance in terms of packet delivery ratio across all mobile sync speeds. When it comes to throughput, also the suggested mobility model achieved high and stable performance for a network comprising 51 nodes under all of the movable sync speeds, consequently decreasing the frequency of updates and potential modification to the routing path. Fixed sensor nodes will also have enough time to transmit data and connect with the mobile sync properly due to the fair length of the routing path. The packet did not have to pass through many hops to be delivered, making 51 nodes network the most performant and stable in all scenarios. Furthermore, the results obtained for the mobility model proposed in this work were compared to another three mobility models, namely uh, depth first mobility model, Gauss-Markov mobility model, and random waypoint mobility model. These models were selected because they have similar behavior. In other words, the movement of the mobile sync is divided into movement periods and pause or sojourn periods. Uh, they differ from the proposed model in the way in which the mobility model is constructed or derived. Uh, for the random waypoint mobility model, it is based on selecting a random direction and a random speed from time to time. For example, when the pause period is over or expires, a random direction will be selected and the mobile sync will be moving towards it in a random speed. Upon arrival of the new location, a pause period is started. On the other hand, the Gauss-Markov mobility model uh, considers various amounts of unpredictability and make the model more realistic. A movable node in this model can adjust its direction and speed as needed, where the mobile node is initially given the direction and speed of motion and moves for a certain amount of time by these parameters. After that, a new course and velocity are determined using values from the previous iteration. So it's not totally random. The result, the parameters values are based on values used from previous iterations. The depth first based mobility model will determine how the mobile sync moves through the network. The movement of the mobile sync is divided into pause and motion periods with the starting node chosen at random. So a starting node is chosen at random, and after that, the network is traversed in a depth first traversal. Upon arrival to a node or near to a node location, the mobile sync will enter a pause period. When the pause period expires, it will go to choose another location based on that algorithm and start moving to it with a specific speed. Uh, After simulating all these networks or these models using the same scenarios, it turned out that the overall performance of the suggested mobility model was better than the other three models because the movement path is predetermined and pre-calculated. Finally, uh, we conclude by saying that the network with 51 nodes produced the most stable and respectable for performance, and the mobility model was recommended to be better and suitable for usage under moderate size and modest speed also. Uh, and when compared to other models, also we obtained almost the same results, uh, and our model outperformed the other three models that were discussed before. And thank you very much.